Good morning, good afternoon, and good evening, everyone. So today, what we're going to be doing is we're going to approximate the second derivative, and we're basically going to use the center difference theorem thing, right? Or scheme, I mean. So or just to briefly recall, what is the center difference scheme? Or if we take the first derivative of that? Well, so we're going to try to approximate it here. I said I was going to do an in-depth derivation of this whole thing. So if my first derivative is approximately my f of x1 plus h over 2 minus f of x1 minus this over h, right? That was my center difference scheme. So if I do the second derivative, here I'm doing implicit differentiation, so I'm also taking derivative of both left and right hand side, right? So let me just do this over h. And then from there, I do a quotient rule. Okay. And so this is going to give me this value, f of x1 plus h minus 2 of f of x1. Then I'm going to add it to f of x1 minus h. And then that's going to be over h squared. And then from there, what will the convergence order be? So here is where our Taylor approximations come in. So just like what we did in the previous derivation of approximating using Taylor approximations, here we're going to do the same thing for each term. So for the first term, we want to identify what the convergence will be. So previously, when we approximated derivatives, we got a convergence rate of 2, right? Which is quite faster than the limit definition without the limit, right? It's quite faster than that. So here, let me go ahead and do this. So this is my first term, right? And doing a Taylor approximation would be like this: f of x1 plus h, then the derivative of this thing, and then h squared, h over 2, h squared, then my double derivative at that point, and then cube, and then 4, and so on and so forth. Cube, then this is factorial. F this, then I keep going for factorial, right? Oh, and then this is my error term, right? And then from there, I keep going. So now this is my f of x1 minus h. So this is equal to, we do it again, f of x1. But here, instead of adding, we're going to subtract this part, apparently. So let me just do this. And then we're going to add, but this time this is negative h squared over 2. Still second derivative though. Then we keep going until we reach, okay, so this is my error term sub 1, because I have an error term sub 2 here, right? So I keep going. So here I go. Cube 3 factorial, I believe. And this is where we do the factorial. This one. Then lastly, we just do it again for the fourth time. And then this is my error term, or my second error term, right? And now, so what's the big deal behind all of these? Well, this is basically if we add all of those things, so we basically derive them, we get something like this. So here's what's happening. We're going to add all of these this Taylor approximation to here, minus 2f of x1, plus this Taylor approximation. We do all of that stuff, very, very messy stuff. And we should be able to get this one, f double prime x1. I don't want to go in depth on everything because Taylor approximation is something I have yet to look at personally. This is to the fourth. And then I believe this was an error term. Yes, that's an error term. And then the other one here, which is that other error term. And then that's going to be, so this whole thing multiplied by h squared over 4 factorial. Apparently that's how Taylor approximation works. This is my error term. And this error term is basically, oh, look at that, big O of h2. And so my convergence rate is order 2. So kind of similar when it's approximating the first derivative using Taylor approximations. But what if we want to approximate the double or the second derivative using different terms? Right? So we want to approximate, what do we mean by different terms? We'll see it here. I also don't know. Using different terms. So here I'm kind of just touching surface level of what these are. So here, okay. Let's say we have different terms. So f double prime. This is some constant a. And I think this was, yeah, this was x1. Then some other constant, x1 plus h. Then some other constant, 2h. If I do that, well, we can use again Taylor approximations to get an even more accurate approximation. So we're basically using Taylor approximations on each of these. That's going to be, oh, this one's the same. A of f. Yeah, this one's the same. And then what else? B, okay, B is a bit different here. So B of this thing. So using Taylor approximations, there we get B of f of x1 plus B of h. Now I have an h. And then I think this is a derivative, right? Oh, it is. So here I do this. Okay. And then this one is b h squared over 2. Then this is the second derivative. Then I keep going. Then this is 3. Okay, let me just extend towards here. 3 factorial. This is f of 3. And I keep going. So that's infinite stuff. And then same goes for c, which is, this is 2h. We also do a Taylor approximation here. So we're going to get, again, c of this term. We add it to c of 2h. And then my f prime. And then we do it again. So here, oh, that's interesting. I think, okay, so my teacher messed up. So this is supposed to be c of, I think this was 2h squared over 2. Then double. Then lastly, c, then this is 2h cubed 3 factorial f3. And I go all the way infinitely, right? And here we can see that, okay, let me see. So 3 variables a, b, c, we can actually make equations out of these, right? How do we make equations? Well, let's look at each of them carefully. Let's solve this part. This is an equation. We can do that. Another equation would be, oh, so apparently this is b. For some reason, I don't know why that's b. Sus. But okay, that's b. So apparently, okay, I thought my teacher messed up. But apparently this is b. For some reason, I don't know. I haven't done Taylor approximation before. This one's this. This one's this. Right? Then I leave the third derivative out of there. So we can make 3 equations here. So the 3 equations are going to be as follows, right? So here we have a plus b plus c equals 0, right? Then for our blue one, we have bh plus 2 or c2h or 2ch equals 0. And then lastly, this one's a double derivative. So b over 2, bh squared over 2. I add that to c over 2 for h squared. This is equal to 1. Okay, maybe something to do with Taylor approximations. I'm, again, not super sure. Yeah, those are the 3 equations though. And from there we can simplify. And so we actually did simplify. So this simplifies to what? Well, this is the same. This one's different, to b plus ch. This one's also different, b over 2. Plus, I think this was c or 2c. And then this one was 1 over h squared, right? And then from there, I solve these systems of equations, and I will get something like this. Oh, there we go. For my a, I get 1 over h squared. For b, I get negative 2 over h squared. For c, I get 1 over h squared, right? So I'm getting everything in terms of h in this case, right? And then from there, we can use these coefficients. So how would that look like? We're going to use these coefficients. So this would look like this. F of x1 minus 2 f of x1 plus h plus f of x1 plus 2h. Now you might be wondering, where in the world did I get that? Here. 1, negative 2, 1. 1, negative 2, 1. Now you might be wondering, where's the h squared? Well, it's at the bottom. It's here. Okay? And then this is basically equal to my double derivative. And then this is my big O notation. And so here, surprisingly, we get an order 1 convergence. What does that mean? could we find it such that it is order 2? Well, we cannot. But the moment that my ph cubed over 3 factorial plus c2h cubed over 3 factorial is 0, then by chance it would be an order 2. But we cannot impose it on, then we would have an overdetermined system, right? Okay, let me go ahead and get some exercises. Mhm. Or at least like an easier way to explain it, maybe. So that's our formula. This is our formula here. Okay, let me actually. Yeah, what does it mean to have an order 1 convergence? I'm also asking that. It's how quickly the error decreases as the step size h gets smaller. And so what basically happens is that the moment my order is 1, then we can have or cut h in half, and that makes it twice as small, which cuts the error roughly in half. But if we have a convergence error of 2, then this cuts the error to about 1/4. So for, let's say, for order 1 convergence, if we make our h 10 times smaller than what it initially was, then my error will also be 10 times smaller. And this is apparently slower than second order. So doing a second order approximation is actually faster. And it's better in terms of accuracy and step size. But again, it depends on the problem again, right? Depends on the problem and how we go about it. Okay, let's do an exercise 1. So here, I'm gonna hop straight into exercises. So here we're gonna focus on the formula, mostly that formula using central difference. So we're gonna focus more on this central difference formula, the one I just highlighted basically. So what in the world is this? So let me, okay. So if we do this, let's say my function again is a sine of x. And let's say my x is at pi over 4. And then my h, or my step size h, is at 0.1. And then the central formula again, when we approximate, it's f of x plus h minus 2 of f of x, I think, plus, yes, f of x minus h over h squared, right? So here we're going to compute the approximation at x equals pi fourth. And then we're going to compare it to the exact value. And then we're going to compute the absolute error. So doing that, let's quickly do it. So here, the approximate second derivative, if we plug it in, this is pi fourth. So this is my sine of pi fourth plus 0.1 minus 2 of sine pi fourth plus sine pi fourth minus 0.1 all over 0.1 squared. And this will give me around some value that I don't know. Gives me apparently around negative 0.7065. I'm not sure. You guys can check it out for yourselves. Should give around that number. The exact derivative would just be cosine pi fourth, which is around like negative 7071, which is extremely close, I would say, right? It's extremely close. Yes. With our second derivative approximation. And then let's compute the absolute error. So here my error again is this number minus this number. So here just add. And that's again around 0.00059. So it is extremely close, I would say. Very, very, very close. And this shows that the central difference method gives a very accurate approximation with a small step size. And if we try smaller each values, then we'll get better and better approximations. So again, it's this idea of approximating because we cannot solve everything analytically. Sometimes we have to give approximations. Okay. Let me do, okay, there's some error behaviors here. Noisy data, right? We can also do it with noisy data. I'm gonna do exercise 2 and then we're done. Because I just wanna at least get into the basics. Just the basics. I'm not looking to expand from there right now. Okay, so here is the second exercise. Here we're gonna be encountering uneven spacing of data. So let's say, okay, we have f of x as a natural log function. We want to approximate f prime of x at x equals 2. And we're going to be using 3 points. So we're using f of 1.8, f of 2.0, that's 2, and then f of 2.2. And we can make use of this central difference formula. Oh yeah, our h is also 0.2. So the way we can do this is, okay, let me see. Oh, we used finite difference formulas. Okay, here's what we did. So using our central difference formula, we're saying that my f of x plus h is basically going to be my f of 2.2. My f of x is basically going to be my f of 2. And then my f of x minus h is basically going to be my f of 1.8. right? And then from there, I get these points. I get ln of 2.2, ln of, oops, that's ugly, ln of 2, ln of 1.8, right? And then if I approximate those values, I get these, like 0.788-ish. This one is 693-ish. And this one's like around, what, 0.588? Yeah. And then if we apply the central difference formula, we're basically going to get, so using that central difference formula, we're going to get around negative 0.25125, right? And then if we want the exact derivative, well, it's just getting the derivative of this thing. So if we want to get the exact, well, we get 1 over x squared. I think there is a minus there, if I'm not mistaken. And then this will give me, so at f double prime 2, it's going to give me that value, so minus 1/4, which is negative 0.25. And then when we calculate the error, well, it's just the absolute value of both of these stuff. And that's around like what, 0.00125-ish. Okay. And so we're getting very, very close. Again, that idea of getting very, very close to the second derivative using Taylor approximation. So that's basically the idea of it. We just derived that whole thing. Okay, so that's it for this video. We just basically derived how to approximate second derivatives, and we tried to apply it by giving some basic elementary functions and how we would see it when we apply those approximation methods instead of getting their exact derivatives analytically. And yeah, we can see that as our h gets closer and closer to 0, we're getting better and better results, or we're converging to a solution. So that's that idea of numerical methods. It's getting better and better results, not the exact results, but getting better and better results as we change some value, right? So yeah, I hope you guys enjoyed, and I'll see you all in the next video.